Good morning, everyone. Now we are going to start new topic of chapter surface chemistry, and topic is types of catalysis. Catalytic reactions can be divided into two types. One, homogeneous catalysis, and two, heterogeneous catalysis. Now first, homogeneous catalysis. When the reactants and the catalyst are in the same phase, the catalysis is said to be homogeneous. The following are some examples of heterogeneous and homogeneous catalysis. First example of homogeneous catalysis: oxidation of sulfur dioxide into sulfur dioxide with oxygen in presence of oxide of nitrogen as the catalyst in the lead chamber process. The reactants, products, and catalyst are in the gaseous state. Now, second reaction of homogeneous catalysis: hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. Third reaction, hydrolysis of sugar is catalyzed by H plus ions furnished by sulfuric acid. Now second type, heterogeneous catalysis. The catalytic process in which the reactants and the catalyst are in different phase is known as heterogeneous catalysis. Some examples of heterogeneous catalysis. Number 1, oxidation of sulfur dioxide into sulfur trioxide in the presence of platinum metal or vanadium pentoxide as catalyst in the contact process for the manufacture of sulfuric acid. The reactants are in gaseous state while the catalyst is in solid state. Second reaction, combination between nitrogen and hydrogen to form ammonia in presence of finally divided iron in Haber's process. Next, oxidation of ammonia into nitric oxide in the presence of platinum gauze as a catalyst in Ostwald process. Next reaction, hydrogenation of vegetable oils in the presence of nickel as catalyst. Now, other topic, characteristics of catalysis. Characteristics of catalysis are: number 1, a catalyst remains unchanged in mass and chemical composition at the end of the reaction. Second, the catalyst cannot initiate the reaction. The function of catalyst is to alter the speed of the reaction rather than to start it. And third characteristic, the catalyst is generally specific in nature. Fourth, the catalysts cannot change the position of equilibrium. Fifth, catalytic promoters, substances which themselves are not catalysts, but when mixed in small quantities with the catalysis increase their efficiency are called as promoters of activators. Sixth characteristic, substances which destroy the activity of the catalyst by their presence are known as catalytic poisons. Seventh property, change of temperature alters the rate of catalytic reaction as it does not for the same reaction in absence of catalysts. Next topic, absorption theory of heterogeneous catalysis. Heterogeneous catalytic reactions generally proceed via absorption of reactants on the surface of the catalyst. Mechanism of such surface reactions may be explained in the terms of diffusion theory of catalysts. This theory postulates the following sequence for gaseous reactions on a solid surface. 1. Diffusion of the reactants to the surface. Second, absorption of the reactant molecules into surface. Third, actual chemical reaction on the surface. Fourth, desorption of the products from the surface. Fifth, diffusion of the products away from the surface. In generally, step 3 determines the rate of reaction. However, step 2 and 4 may be rate determining. Now, enzyme catalysis. Enzymes are complex nitrogenous substances secreted by low forms of vegetables and organisms. Enzymes are actually protein molecules of higher molecular mass. Enzymes from colloidal solutions in water and are very effective catalysts. They catalyze numerous reactions, especially those connected with natural processes. Numerous reactions occur in the bodies of the animals and plants to maintain the life process. These reactions are catalyzed by enzymes. The enzymes are termed as biochemical catalysis, and the phenomenon is known as biochemical catalysis. As for example, nitrogenase. Nitrogenase is an enzyme present in the bacteria on the root nodules of leguminous plants such as peas and beans, catalyzes the conversion of atmospheric N2 to NH3. In the human body, the enzyme carbonic anhydride catalyzes the reaction of CO2 with H2O. The forward reaction occurs when the blood takes up CO2 in the tissues, and the reverse reaction occurs when the blood releases CO2 in lungs. Thus, the enzyme catalyst reactions take place into two steps. Now, activity and selectivity. Activity and selectivity. Activity. Activity is the ability of the catalyst to accelerate chemical reactions. The degree of acceleration can be as high as 10 raised to 10 times in certain reactions. For example, reaction between H2 and O2 form H2O in presence of platinum as catalyst takes place with explosive violence. In absence of catalyst, H2 and O2 can be stored indefinitely without any reaction. Now, selectivity. Selectivity is the ability of catalysts to direct reaction to yield particular products. Now, zeolite shape selectivity or shape selective catalysis. Zeolites are aluminosilicates of the general formula Mn ANO2X SiO2Y MH2O. Here, M may be simple cation like Na, K plus or Ca plus, and small n is the charge on the simple cation, and small m is the number of molecules of water of crystallization. They have honeycomb-like structure called beta cage. The reactions catalyzed by zeolites depends upon the shape and the size of the reactant and product molecules. That is why these types of reactions are called shape selective catalysis. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in the petroleum industries is ZSM5. Z means zeolite, S means sieve, and M means of molecular positivity 5. It converts alcohols directly into the gasoline, means petrol, by first dehydrating them so that a mixture of hydrocarbons is formed. Catalysts used in industries. Haber's process is used for manufacture of ammonia. Second, Oswald's process for the manufacture of nitric acid. Contact process for the manufacture of sulfuric acid. Bosch process for the manufacture of hydrogen and Deacon's process for the manufacture of chlorine. Synthesis of methanol and hydrogenation of vegetable oils. Now, new topic, colloidal state. The colloidal state depends on the particle size. It is regarded as intermediate state between true solution and suspension. Now, what is true solution? In true solutions, the size of the particles of solute is very small and therefore these cannot be detected by any optical means and freely diffuse through membranes. It is a homogeneous system. And suspension. The size of particles is large and thus it can be seen by naked eye and do not pass through filter paper. It is a heterogeneous system. Now, dispersed phase and dispersion medium. First, dispersed phase. It is the component present in small proportion and is just like a solute in a solution. For example, in the colloidal solution of silver in water. Now, dispersion medium. It is generally the component present in excess and is just like a solvent in a solution. For example, in the colloidal solution of silver in water, water acts as a dispersion medium. Classification of colloids. Classification based on the physical state of the dispersed phase and dispersion medium. Depending upon the physical state of dispersed phase and dispersion medium, whether these are solids, liquids or gases, 8 types of colloidal system are possible. Different types of colloidal system. Like number 1, aerosol of liquids, as for example fogs, clouds, mist, fine insecticide sprays. Second system, aerosol of solids, as for example smoke, volcanic dust, haze, foam or froth soap leather. Third system, emulsions, example milk, emulsified oils, medicines. Next system, sols, example most paints, starch in water, proteins, gold sol, arsenic sulfide sol, and ink. Next system, solid foam, pumice stone, styrene rubber, foam rubber. Next system, gels, example cheese, butter, boot polish, jelly, curd. And eighth system, solid sols, means colored glass, example ruby glass, some gemstones, and alloys. Classification based on nature of interaction between dispersed phase and dispersion medium. Lyophilic colloids, that is water loving. The colloidal solutions in which the particles of the dispersed phase have a great affinity for the dispersion medium are called lyophilic colloid. Now, lyophobic colloid, that is water heating, the colloidal solution in which there is no affinity between particles of the dispersed phase and dispersion medium are called lyophobic colloid. Classification based on types of particles of dispersed phase. Depending upon the types of the particles of the dispersed phase, the colloids are classified as multimolecular colloid and macromolecular colloids. Now, new topic, micelles. Micelles are the clusters of aggregated particles formed by association of colloid in solution. The common example of micelle are soaps and detergents. The formation of micelle takes place above a particular temperature called Kraft temperature and above particular concentration called critical micellization concentration, means CMC. They are capable of forming ions. Micelles may contain as many as 100 molecules or more. For example, sodium stearate is a typical example of such type of molecules. When sodium stearate is dissolved in water, it gives Na plus and stearate ions. The stearate ions associated to form ionic micelles of colloidal site. It has long hydrocarbon part of C17H35, which is lyophobic, and COO minus part, which is lyophilic. Next topic of cleansing action of soaps. When oil droplet comes in the contact with soap solution, the stearic ions are arrange themselves around it in such a way that hydrophobic parts of the stearic ions are in the oil and the lyophilic in fact, the stearic ions of soap molecules help in making a stable emulsion with water, which is washed away with the excess of water. It may be noted that a sheath of negative charge is formed around the oil globule. Now, new topic, general methods of preparation of colloids. Lyophilic and lyophobic colloidal solution are generally prepared by different types of methods. First, preparation of lyophilic colloids. The lyophilic colloids have a strong affinity between particles of dispersed phase and dispersion medium. These colloidal solutions are readily formed by simply mixing the dispersed phase and dispersion medium under ordinary conditions. For example, the substance like gelatin, gum, starch, egg, albumin pass readily into water to give colloidal solution. They are reversible in nature because these can be precipitated and directly converted into colloidal state. Now, preparation of lyophobic colloids by oxidation. Number 1, a colloidal solution of sulfur can obtained by bubbling oxygen through a solution of hydrogen sulfide in water. Second, by reduction. A number of metals such as silver, gold, and platinum have been obtained in colloidal state by treating the aqueous solution of their salts with a suitable reducing agent such as formaldehyde, phenyl hydrazine, hydrogen peroxide, stannous chloride, etc. By hydrolysis, many salts are rapidly hydrolyzed by boiling dilute solution of their salt. For example, ferric hydroxide and aluminum hydroxide salts are obtained by boiling solution of the corresponding chlorides, means ferric chloride. Similarly, silicic acid salt is obtained by hydrolysis of sodium silicate. And fourth, by double decomposition. A sol of arsenic sulfide is obtained by passing hydrogen sulfide H2S through a cold solution of arsenious oxide in water.